Welcome everyone to this seminar. We are happy to host Kishor Jothimurugan, who is currently unaffiliated, but who is who is an alumnus of CMI. He did his bachelor's here, and then he went on to do a master's plus PhD at University of Pennsylvania with Rajiv Allur. So he's been working on the intersection of formal methods and machine learning. Very interesting questions that we've been looking at. And now, as he tells us, he's an incoming researcher at, he will be joining 2 Sigma. So before I'm not sure whether he's going to formal methods after this. Before he he leaves it, let's listen to him. Let's listen to what he has been doing. So over to you, Kishor.
Yeah, thank you. So I was a PhD student at Penn, so I'm going to talk about basically my thesis, which is on specification-guided reinforcement learning. I thought I would start with a brief background on reinforcement learning. So you might have heard that RL is a tool. It's a part of machine learning, and it has been used successfully in many recent AI applications. For example, OpenAI used it to solve Rubik's Cube using a robotic hand. It is used in training ChatGPT, GPT-4, and whatnot, and also in beating humans at the game of Go, chess, and many others. So in the setting of reinforcement learning, we usually have some agent interacting with some world, and this world is usually modeled as a Markov decision process. So what happens is that the world is in some state S. The agent observes this state, takes some action in this world. And once the robot takes the action, the system changes state, and this transition is usually probabilistic. So there is some distribution over next state S prime. And once the system changes state, the robot observes the new state. Now it can take another action, and this process sort of keeps repeating forever. And the usual way to train agents or to make agents behave a certain way is to give them some reward signal. So this is the R here. So it's a real number telling how good it did in the current interaction. And it keeps getting this reward for every interaction. As I said, the setting here is that the system is probabilistic. However, the model of the environment is unknown. What I mean by that is that you don't have the MDP with you, so you don't know what the distribution of next state's S prime is given the current state and the action. That is something that you have to infer by interacting with the world. So that's where the learning part comes in. And the goal is usually to learn to act in this environment so that you maximize the aggregate of some aggregate function of all the rewards received over the infinite duration that you're interacting with. And it's usually the expectation of this aggregate reward because the system is probabilistic and you have a distribution over this rewards.
So Kishore, the reward is part of the Markov model?
Let's assume not for. I mean, usually that's how it's done in RL, but in this work we'll not do that. So we want to remove reward. So I'll get to that. But I'll get to that. Reward is, let's say reward is the specification for this, right? So I can illustrate this using an example. So let's say we have this this maze of rooms, and then this robot is there in some corner. And then you have some goal region, which is the green box. And then you are not allowed to enter this red region, which is, let's say, an obstacle, right? So here we would model the state of the system as simply a vector in R2, right? And the action, let's say, for simplicity, is the velocity vector, which gives the velocity with which the robot will travel for the next time step, right? Let's say 1 second. And upon taking this action, there is some transition, and this transition is according to some distribution P. And here it can be as simple as a normal distribution centered at the new location you would reach if you actually follow the velocity vector starting from the current state, right? I mean, this is sort of a made up example. You might not have a clear distribution like a normal distribution, but there will be some noises in the environment which will not always take you to x plus vx and y plus vy. You will end up in some nearby state, hopefully, right? So this is the model of the environment itself, and this P is something that you do not know, but you know what the state space and the action space are and all that. And now let's say we want to train a controller, or we want to find a policy to make the agent reach this goal, right, without hitting the obstacle. Then in order to use existing RL tools, what you would do is you would go and write some reward function that gives a reward value for every step of interaction. So this can be as simple as giving a -100 on hitting the obstacle, giving some small positive reward for reaching the goal, and 0 at all other intermediate steps, right? And if you manage to write a reward function, then you can use existing RL algorithms. And what this algorithm will output is a policy mapping states to actions. So here it will be, let's say, a neural network mapping R2 to R2. And the objective is to usually maximize the expected value of this discounted sum reward, right? So it maximizes over infinite time steps the sum of gamma to the t, where gamma is some discount factor of the reward at time step t, right? Does that answer your question, Deepak? I can.
So, okay, so the normal RL algorithm will, I mean, this reward is part of the model, is it?
Yes, for a normal RL algorithm, what you need is that you need to know the state space, action space, and with every step of interaction with the environment, you need to give the algorithm back what the new state you reached is, and what the reward for that step is. So this is it's sort of in an online way, you're just giving feedback to the algorithm saying, okay, you took this action in the state, this is where you ended up, and this is the reward that you achieve for this step. And you need to do this for every step. That's the model. That is the model that's usually required of RL.
So the RL algorithm learns this policy that maximizes the expected reward.
Yeah, that's how the RL problem. Yeah.
Without knowing the Markov model and the reward.
Yeah. So the reward, it sort of, yeah, both reward and the transition probabilities, it sort of learns by interacting with the environment. So it keeps interacting, and then it builds a model itself, or maybe not, but by more interaction, it gathers more information about the environment. So then it can make better decisions over time.
Okay.
Okay. So yeah, so that's RL. Very brief introduction, no details there. But this work is focused on addressing some of the challenges in reinforcement learning using formal methods, right? And I would like to elaborate on these challenges first. Firstly, assigning rewards is a hard problem. So if you remember, RL was initially applied to solve games like blackjack and so on, and then more complicated games like Atari and so on. So it's very clear what the reward here is, right? So if you're playing a game, the game has some score. You can just give the score that you achieve at every time step as the reward, and everything works fine. But in more recent applications, you might have noticed that RL is being used in training controllers for these complex robots, such as this robotic arm. And what often happens is that there is someone who's trying to write a reward function to achieve a certain objective, and then that is used to learn the policy, right? So ideally, let's say for this robot, we want to say that the robotic arm must get close to the block, pick up the block, and then move to some target and place it. It's very natural to think about it temporally and say, okay, these are the things that it should do, and things like that, instead of writing one reward function saying, okay, at every step, what reward should I give, right? And it is also very easy to misspecify what you want using rewards. So here is an example. So reinforcement learning algorithm was used to learn to drive this robot around a track, which is marked by this yellow border. And it also gets some bonus for hitting these green objects. And there is some penalty for hitting the other boards and walls and whatnot. What happens is that the way the reward was written, it looked very natural, but what happens is that it ends up hitting these bonuses more often than it would if it actually followed the track. And then, but as a result of that, it actually ends up crashing quite a few times. And this is not something that the user intended, right? So it's a very cumbersome process to write reward functions, and often you have to write one thing and then see how it works, and then change the reward function again until you get the behavior that you're sort of satisfied with. I mean, as an exercise, you can even ask ChatGPT why reward engineering is hard, and then it somehow knows the answer. It says, a reward function needs to be adjusted and fine-tuned over the course of training, and it's often hard to balance short-term rewards, which is step-based rewards, with long-term objectives that we are trying to learn policies for. So yeah, so the challenge here is that the need to write rewards really hinders the usability of reinforcement learning as a tool. And so what people have done is that, okay, now we know how to specify things using temporal logic. Let's try using temporal logic to specify rewards instead, and somehow generate rewards automatically from this specification, right? So instead of writing rewards, what you would write is some temporal specification, let's say an LTL specification, and then there would be some algorithm that would take the specification and give you some reward function. But what often happens with this line of work is that the reward that you get out of such algorithms are sparse, in the sense that you only get some reward signal once you actually achieve some goal. For example, in the case of the robot example I showed, you'll only get a positive reward when you actually hit the goal, and then you are just getting 0 everywhere else. So this is not good, because when you're actually trying to learn, all the agent sees or the algorithm sees is zeros until it eventually somehow finds a way to reach the goal, right? So you're not really guiding the algorithm to learn the behavior, and you're just hoping that it would stumble upon the good behavior, right? So it's not often just sufficient to generate correct rewards for a specification, but you also need something that enables better learning. Now, let's somehow assume that we have a reward function, and it's also good, it's correct, and whatnot. In spite of all that, the RL still doesn't work for some scenarios, because the current RL algorithms are primarily designed to tackle short-term objectives in complex environments. So what I mean by that, so if you look at the robotic arm example, then you can train how to reach certain parts of the table. But if you want to do multiple things like stack objects on top of each other, these are sort of tasks that RL is not currently very good at. So I can illustrate this using a very simple example. Let's say we are in that robot maze scenario, and let's say the robot starts in this blue box denoted by S0, and the goal is simply to visit S1 or S2, which is the top left or the bottom right, without hitting the obstacle, right? This is your objective, and you can try writing reward functions for it, or use existing tools to generate reward functions from temporal specifications. Here, the plot shows the performance of many algorithms. Here, the x-axis is the number of interactions with the environment that you use to actually learn about the environment. And the y-axis denotes the probability with which the specification is met by the policy that the algorithm learned. So the algorithm learns a policy over time, and then this policy keeps evolving. And over time, you hope that the success probability also increases. And this is fine. There are existing approaches that can do this. However, if you modify this objective and say, okay, now I want to visit S3 in the end, then what happens is that most algorithms still learn to go to S2 because there is no obstacle on the way. And they just never learn to try to go to S1 because it's just easier to get to S2. And then they get stuck because there is no direct path from S2 to S3, and the doors are all closed, right? And the same algorithms don't do that well. And you can try a bunch of reward functions and it still doesn't work quite well. I mean, you can theoretically learn how to do this with existing algorithms because there are convergence guarantees, but then you would need a lot more samples and a lot more time to actually learn how to do this. So the challenge here is the training policy for complex tasks requires a lot of samples and time and computational resources and so on. And finally, RL is typically used in conjunction with neural network policies in continuous state and action environments. So, if you're interested in applying RL to learn policies in safety critical scenarios, you might want to verify that the policy that you learned is actually safe and whatnot. So let's say you are interested, you used RL to learn.
Kishor, just sorry, one question. In the
Yeah.
previous slide, when you were saying that you want to go from S0 and you want to visit this S3 via S1 or S2, so what is the probable path? It seems like you have to visit that O anyway, right? Because
I mean, so this is a continuous state environment, so you can go around the O.
or you can go around the black walls also, or maybe.
No,
or
the
maybe
walls are walls, and then the rooms are. So imagine this as a 2D
I
state
see,
space,
I see.
and then
Okay,
certain
okay.
parts of the state space are not allowed
It's a
to go.
continuous, I see. Okay, okay. Thanks.
Yeah, you can control the robot to go around the obstacle, but it's just harder to learn that behavior, and it's easier to make progress by visiting S2, right? So
Okay.
yeah. Although it is not really progress for this specification, which is what our algorithms don't realize that easily.
Okay.
So yeah, so let's say somehow you learned a neural network controller to control this car around this particular racetrack. And now you want to say that the car will never leave the track, right? The way you would verify this, at least with existing algorithms prior to our work, is to over-approximate the set of states reached, right? So let's say this gray box denotes the set of safe states or the states within the track. And the blue circles denote the actual set of states that you can reach at various time steps. Then you would just over-approximate this over time. And what happens is that when you're trying to over-approximate this using existing algorithms, the approximation error sort of increases over time. So if you want to say something for a very long time period or like infinite time duration, then it's not possible using existing algorithms. And you end up over approximating too much and not really, you won't be able to verify that you are within the safe set. Although in this case, the car is safe, right? So scaling verification to such long horizons and complex tasks is again a challenge. So these are the main challenges that my work tries to address. So I have worked on theoretical frameworks for modeling reinforcement learning problem using temporal specifications. So going away from the standard model of rewards and trying to use LTL. And so there are some research showing certain things are not possible, and pack learning is probably not the right framework to study these things in, and so on. And then this work on Spectral tries to actually design a simple specification language to specify some tasks in the robotic setting. And then it provides a way to actually automatically generate rewards, but these rewards are not sparse or they are actually rewards that guide the learning algorithm. And then this work tries to, not just take the specification and convert it to rewards, but rather modify the learning algorithm itself to improve the performance. And there is an extension to the multi-agent setting, and finally also worked a bit on the verification part, trying to scale verification to complex tasks. And in this talk, I'm going to focus on these three works, with most of my time spent on the number 3 thing. But I mean, I can go into details of anything that you are interested in, and you can stop me in the middle if you feel like. So before that, are there any questions about the RL setting or the challenges? Okay, good. So yeah, so first, so this is our very initial work on trying to use temporal logic for specifying reinforcement learning tasks. So our logic is sort of loosely based on LTL, but it doesn't have the full expressive power of LTL. So we have some predicates which map states to true or false. And for example, you might have a predicate visit S1, which is just true at all states in S1 and false outside. And the tasks you can specify using this language are as follows. So this is the syntax. You can say eventually B, which says that you should eventually, reach a state where B is true. This task says that you need to do task phi, but also ensure that at every time step you are in a state that satisfies predicate B. So this is like a safety constraint. And phi1 followed by phi2 just says you need to do phi1 first and then phi2. And then disjunction is this disjunction, right? So if you go back to the example, if you want to say visit S1 or S2 while avoiding O, you would encode it as follows: say eventually visit S1 or eventually visit S2, ensuring avoid O, where visit S1, visit S2, avoid overall predicates that you design. And the typical goal in reinforcement learning is to maximize the expected reward, but here our goal is to maximize the probability that you satisfy the specification. So if you take a policy, you have some distribution over runs, since it's an MDB, and then you can measure this probability of satisfying the specification, and you want to maximize that.
So what is the semantics of the semicolon?
So it's you should do task phi1 followed by phi2. So more technically, you split the run into 2 parts. The first part satisfies phi1, the second part satisfies phi2. That's it.
Okay.
It's like it's concatenation in regular
like
expression.
Chop, I think chop and duration calculus.
Yeah, or you can also think of this as eventually.
Is it until? It's until, right, Deepak?
Phi1 followed by phi2 is not until, really. Phi1 followed by phi2 is a nested eventually. So it's an eventually B1 and eventually B2. So B1 and eventually B2 inside another eventually. Does that make sense? You can think of it that way.
It'll be like two eventually.
Or you can also think of it as just concatenation regular expressions. That's much easier to think about. Right? It's just 2 parts of the string. One part satisfies phi1, the other part satisfies phi2.
So how did you say you can express it using eventually?
So it's eventually brackets. Inside the bracket, let's say you have B1 and eventually B2. Right? So you must eventually reach a state where B1 is true, and at that point, you want eventually B2 to be true.
So, but phi1 might be a continuous thing, or not just eventually B.
Yeah, sure. No, I'm simplifying it. Yes,
Okay.
You're right. phi1 might be something complex. But
okay,
I mean, the easiest way to think about it is just concatenation, right?
Okay, but is this a subset of LTL?
Yeah, you can express everything. I mean, yeah,
Okay,
it's a complex
fine,
combination thing, but you can express everything using LT.
So that example you mentioned regarding first visit S1 or S2 and then visit S3, right? So this can be specified as a composition, right? if I'm not
Yeah.
mistaken.
So you have this, right? The current thing, and then you'll add a semicolon and write eventually visit S3.
Right. Thank you.
Yeah. Okay. Okay. So moving on, how do we learn policies for such specifications using RL, right? So the first step is to construct some sort of an automaton, and this step we call it the decomposition step, that takes the specification and really just like clarifies what the subtasks are, what are the simple small things that needs to be done in order to do the overall thing. And then you learn one neural network policy to perform each of these subtasks. So subtasks might be like just go there or do this, something small. And this you can use off-the-shelf RL because these subtasks are of a specific kind for which we sort of figured out how to generate rewards that work well from the specification. And then once you learn the subtask policies, then you sort of use some high-level planning algorithm to compute the best sequences of these policies to execute or best sequences of subtasks to perform in order to do the overall thing, right? And this process is sort of like interleaved. So the learning step gets feedback from the planning and the planning gets feedback from the learning and so on. So the first step is the decomposition step. So in the decomposition step, what we construct is called an abstract graph. So if you go back to this example of visiting S1 or S2 and then S3 while avoiding O, the graph will look something like this. So the graph, in the graph, each vertex is simply a set of states, right? So the set of states basically some region in the state space. And each edge represents a subtask. So this particular edge says that you need to visit some state in S2, starting at any state in S0, right? So it's sort of a reachability task. And you also have some constraints on the edges. So these are sets denoting what sort of runs or trajectories are safe for doing this subtask. So here the constraint is that the trajectory must never hit any state within this region, within this red region, right? And then there are some final vertices, and if you reach a final vertices, then it sort of then it signifies that you have completed the overall task, right? I hope that makes sense. So what we are trying to do is trying to do a bunch of reachability tasks on this graph, where a reachability task is simply an edge. And we want the edges to form a path from the initial state to some final vertex. So the problem reduces to this, which is to compute policies that look like this. So we have a policy, we call these policies path policies, which consists of a path, let's say S0, S2, S3, from the initial vertex to a final vertex, and one neural network for each edge on this path, let's say pi1 and pi2, to do the corresponding tasks. So pi1 is trained to reach S2 and pi2 is trained to reach S3 while always avoiding the obstacle, right? And the way you would execute this policy in when you're actually deploying the policy is to execute pi1 until you observe that you have hit S2. And if you observe that you have hit S2, then you will switch to this policy pi2 and then start executing that, right? So the problem reduces to computing two things. One is to plan, which is to compute this path. The other is to compute these policies themselves, which is pi1 and pi2 in this case, right? And our algorithm tries to do both simultaneously. So any questions?
Sure.
So you were, yeah, sorry.
Sorry, go ahead.
Yeah, no, it's so the edges have to be simple actions, or can they themselves be the subtask itself be the primitive subtask, or can they include something like eventually something more?
So each subtask is essentially. So the way from our language, what happens is that when we construct this abstract graph, each subtask is essentially just a reachability task with some safety constraints. That's sort of a theorem or whatever, right? I mean, because the language is when you take the language and you define inductively how to construct this abstract graph, what ends up happening is that when you construct the graph, you end up getting the subtasks which are simply reachability with safety constraints. Does that answer your question, or did I understand?
Yeah, I
correctly?
am still not fully clear. I'll take it offline.
Okay, sure.
So yeah, I mean, so this logic, the specification language, as you were saying, that it is a subset of standard LTL. So
Yeah.
is it because that you are considering this specification language, this whole thing cannot be done for LTL, or I mean, can you do
Yeah.
this with LTL specification? The whole thing that you were talking about, this decomposing it into subtasks and then learning for each of them a policy, and then you get.
No, I think the overall like high level idea is probably doable with LTL. We just we didn't focus on LTL because this language was sufficient for like the tasks we were considering, and it is much easier to get this abstract graphs out of the specification than like for all of LTL, right? So
Okay.
yeah, but I think that's something to look in the future. Like, can you actually get these like decompositions if with constraints that all these subtasks must be of a certain kind, right? So our constraint was also like the subtasks have to be of a certain kind so that we know how to generate rewards to learn policies for these subtasks, right? So if you just take LTL and a Buki automaton or whatever, then you might not have this, right? Yeah.
Sorry, I
Also,
didn't get you. You might not have what? Like.
so you may not have this higher level structure. So this is not really an
Okay.
automaton. You don't change
Okay.
states, you don't change vertices
Okay. I
for
see.
every step, right? You
Okay.
change
Okay.
vertices for completing a subtask,
I
and that
see.
subtask is of a very specific kind for which we know how to generate rewards.
I see. Okay. So so I think what I understand is that like for this specification, the task becomes much simpler and easier to sort of.
Yeah, the structure is easier to exploit for learning.
Okay. 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 Thanks.
Yeah, but one problem I was actually thinking about was, if you have an LTL spec and you have, let's say, another, a class of languages saying what are these subtasks that are for which you know how to construct rewards, then can you construct actually an abstract graph like this with each edge denoting sort of a language from this class of languages for which you know how to generate rewards? And I think that's an interesting problem. I don't think that has been studied before. It's sort of but I don't know. I didn't think too much about it, but I was briefly thinking about that problem. But for us, it's all straightforward.
Okay.
Yeah. Any other questions?
So do you in the planning part, you will first find one path, is it like from S0 to S3?
Yeah, I'm going into the details of the
Okay,
algorithm itself. So just like, yeah, I'll go into that. The next slide. Okay, so if there are no other questions, so the way we do that is simple, right? So to compute a path, we simply use Dijkstra's algorithm to compute shortest path, right? But the problem is that we don't have any costs on the edges, right? At least for now. So whenever we need a cost on an edge, so let's say we start Dijkstra's algorithm on S0, it will immediately ask you for costs on these two edges that are going out of S0. Then you go ahead, since you know how to generate rewards for these rewards to learn these policies, you generate the rewards and you use off-the-shelf RL and you learn these policies. And once you learn these policies, you estimate this PI, which is the probability that pi successfully achieves that subtask, starting at some state in S0. And you assign this negative log probability as the cost on the edge. So the reason we do this is simple, right? So when you add up all the costs on an edge, you end up multiplying the probability of successfully doing each of these subtasks, and the negative sign is just to make turn the maximization problem into a minimization problem, which Dijkstra's algorithm handles, right? So let's say this happens, you learn this policies pi1 and pi2, and you get these cost negative log probability 1 and 2. Now you run Dijkstra's algorithm further, then what happens is that it now requires costs on these two edges going out of S1. And one thing that you require while training policies is some way to sample initial states from the set of states. So S1 is a set of states. So when you're training, where do you start within S1, right? So you might start at various different positions. And that actually affects how the algorithm will perform later, because if you always start in like a very favorable state, it doesn't know how to handle when later you end up in some bad state in S1 and need to go somewhere else, right? So, so the distribution that we used to train, distribution of start state that we used to sample.
I had a question. Could I ask, Kishor?
Yeah, sure. Yes.
I'm Raghavan. I'm from ISC.
Yeah.
So one
Sure.
question is, are these S0, S1, etc. the value of that state variable, whatever it is? Is it a...
So this is the abstract graph. I'm sorry if I didn't make that
So
clear.
is it an integer? Is it the value of the underlying state?
No, these are regions. So this is a set of states.
Okay.
So you can think of this S1 as a set of states where predicate B1 is true.
And is that given? The abstraction is given, is it?
The abstraction is from the predicates, from the language. So from the language, you get these states. So these states are always a conjunction of some predicates.
It comes from the given LTL properties.
Yeah, it comes from the property. You construct the graph, and each vertex in this graph is a set of states represented by predicates in the specification.
Okay, and the action is what is the action? How what is the reward? What is the reward? What is the form of the reward?
The reward is some distance-based reward. I guess it uses some quantitative semantics of predicates to generate this reward to learn the policy. So like if you have, if the predicate is, let's say, some variable x less than 2, then I think the reward is like 2 minus x or something.
That will be the learned reward from your system.
That will be the automatically generated reward from the specification for that particular subtask.
Generated by your system.
Yeah. So the algorithm, when it generates this abstract graph, it also generates rewards for each edge.
Okay.
Right. And that is what you use to learn these little policies on the edges.
So the policy is learned by the RL system, right? You don't control that, is it correct?
It's learned by an RL algorithm, right? But I mean, it is influenced by the rewards that we generate,
correct.
The initial state distribution that we use, and so on.
And what does the policy do? It says a policy is a map from state to state, is it? From a
state to actions. So at every state it tells what to do. So let's say you start in some state in S0. And then let's say you decide to execute pi1, right? So let's say you start in little S0, then you will pi1 will tell you what action to take at little S0. Then you will go to some S1 and then S2.
The action is a function from states to states, is it?
Action, you have some actions, right? There's an action space.
Well, how does so given a state and an action?
It's an MDP.
It's a next state determined as a function.
So it's an MDP. So there's a distribution, right? Over next states. So it's it looks something like this.
Okay. Sorry to make you go back. I get it now.
No, it's okay.
Yeah.
So here, right? So there's some P that is governing what.
Yeah, I get it now.
Yeah.
So on the reward you are going to learn, your approach is going to emit it. The reward function.
Yeah, the reward function is sort of going to encode the task of reaching S1.
Right, but your algorithm is going to emit it, is it? The reward function?
I mean, the reward function is used to assign rewards to the RL algorithm to learn this policy phi.
Correct. But my question is your approach going to emit the reward function?
Yes, it is. It's going to you take the specification, you get this graph and reward function for each edge on the graph.
And you're not specified yet, right? How to
Get the
emit the
reward.
reward function?
Yeah, I did not go into the details. So it's not in the that's not part of the slides, but yeah, I can talk about it offline if you're interested.
I see. I mean, maybe I missed something. I thought that was the crux, generating the reward function. That was
Both,
the
yeah.
challenge.
So it's both. So that's like the initial part of this world.
Okay.
But then this is also trying to solve this myopia issue where you sort of have to plan at a higher level to make sure you're trying everything possible at the higher level, right? So yeah,
Oh.
I mean it's both. I'm just focusing on one part of it.
Okay. Okay. Thank you.
So I guess you're aiming to output the kind of global reward function, right? Here you have these local reward functions to go from S0 to S1.
Yeah, so there is no
And
need
S0
for
to S2.
global rewards here. That is the whole point, right? So you only need to generate rewards for this simple tasks, and the algorithm will actually give you a path and a policy for each edge on the path. That is your overall policy for the overall task. So you just keep doing these little policies one after the other to do the overall thing. So you basically stitch these policies together later. Is that,
Okay.
so I mean, if you think about it, here is the code, right? So so the overall policy for this task, right, is to go to S2 and then go to S3. And then the way you would do it is you will use pi1 until you reach S2, right? That is sort of trained to do that. And then after you reach S2, you're going to use pi2 to go to S3. Right?
Okay, but don't
So
you have
your
to
policies,
modify the? Okay, so
there is no global reward. So the final output of the overall algorithm is simply a path and policies for edges on the path.
I see. Okay, okay.
And
So
that
just the policy
dictates
is what.
a global policy, like a big policy that is composed of these small.
Documentation that I sent.
Okay, and that will detect the overall reward function.
Yeah. I mean, there's no overall reward function. There's just the final
So, okay,
policy.
so you're directly learning the policy itself, is it?
Yeah, yeah.
Okay.
So you are using RL only, like off-the-shelf RL only to learn the little policies on these edges. And then, and then you're stitching it together sort of.
And you're saying that the rewards for those little steps are easier to write out.
Yes, exactly.
Okay. Okay.
Yeah. Right. So yeah, so basically yeah. So I was talking about the initial distribution. I guess it's not really that crucial to the overall thing, but then we use some heuristics to generate this initial states when you have multiple paths and so on. No need to get into that. But the theorem sort of what motivates this approach is that in overall, like the optimization objective of Dijkstra's algorithm, which is to minimize the path cost, sort of corresponds to actually maximizing the overall probability that you achieve the goal, that you achieve the overall objective. And yeah, and this basically follows from using like the negative log probability, right? So yeah, so we did evaluation on two environments. One is the rooms environment that I've been talking about. Again,
Sorry,
here
I think I sort of didn't understand the theorem at the end. Could you just maybe repeat explain a bit more?
So at the very end in the inequality, the quantity on the left is the probability that that you satisfy the overall specification, right? And CP is just the path cost of the path that you choose in the end. So sort of
Okay. I see. Okay.
Justifies that the shortest path is sort of what you want, kind of.
And this is the optimal one or something. Does it also say this? That I mean, so I can see that, okay, the algorithm that you have, the shortest path kind of thing, that it satisfies the corresponding policy satisfies this objective with at least certain probability. But I mean, does it also say that this algorithm that you have, or the policy that is being generated by your algorithm, kind of an optimal one, or
actually it is actually not the optimal one in I mean, I can construct scenarios where it is not, but in most practical scenarios it works really well. And even in cases when it's not, you often just have to like split the specification, for example, do some abstraction refinement, and you are good. But I won't go into the details of that. Also, we did not like really work on that idea for reserve. But yeah, we use some heuristics in the middle, so that's why you have this inequality. Like, it's not an equality. Like, yeah. So yeah, so now like if you look at the room's environment, we have this like more complex, bigger environment, and we studied specifications that increase in complexity. For example, this one is just to reach one of the circles from the triangle, and there are some baselines, and the blue line denotes this particular algorithm. And if you make the specification more and more complex by adding more and more things to do, basically by sequencing things using the semicolon operator, then you end up seeing that as the specification becomes more complex, existing algorithms don't really scale that well, right? And this is sort of the most complex specification we studied. And you can also see similar results in this robot environment. Here we encoded tasks that involve picking the object, placing it at different locations, having a choice between two locations and things like that. And here also it does really well. So that summarizes this algorithm. And before I run out of time, I want to briefly go to the verification part of things.
So, Kishor, just a quick question on that part.
Yeah.
So I mean, I'm sure there are techniques like, trying to play games on these stochastic games, and, trying to achieve some winning condition. So,
I mean, yeah.
I mean, I don't know too much about those, but I'm sure that there are these kind of things.
Yeah.
And how would those perform on these tasks that you have? Would they do better than you in terms of more optimal policies? And
I mean, these are MDPs, so there's not really a game. It's just stochastic environment, so it's sort of like a 1.5 player game.
Right, but there are these games on stochastic. I mean, maybe Shivashish knows.
Yeah, but I mean, yeah, the whole problem here is that we don't have the model, right? So if you take an algorithm to solve the game, for example, that algorithm requires a model of the environment, right? What the MDP actually is, right? Does it make sense?
Okay.
And
so
also,
you're saying that the algorithm here doesn't have the model.
Doesn't have the model. These environments are continuous state, continuous actions. So the state of this robot is some vector in I think 22 dimensions, something.
Okay,
right?
But maybe you could compare the optimality of your algorithm with those.
Yeah, I mean, you need to abstract away and make it a finite state environment, right? In order to really use those algorithms.
I don't think they need. Yeah, but okay. Anyway, maybe we can.
Or some way to like model it in represent the continuous state model in a finite space, right? Yeah. Like some functions.
Yeah.
Right? Yeah. Anyways, so I'm going to move directly to the verification part, because this is a verification seminar. So yeah, so the main advantage of the way we do things is that we don't have a single neural network policy to do the whole thing, right? we have a bunch of small policies to do the small things, and we're just stitching them together. So this naturally motivates us to consider verifying also in a compositional way. You're only verifying these small policies for these small tasks and somehow stitching the verification results to prove something about the overall system, right? So that sort of motivates this work where, so we look at this F110th car. So this is like an autonomous car. And the way this car reads the environment is using a LiDAR sensor. So it has the sensor on the top. It sends rays in all directions. And then, this ray, and then it observes the distance to the closest obstacle in each of these directions. And that's sort of what it observes. It doesn't know the actual position of the car and so on. And the controller takes this LiDAR reading and then outputs some action, which is, the steering angle and the throttle and things like that. And this problem is it's a challenging control problem for solving using traditional control techniques. And this particular video shows the car being controlled by a neural network controller trained using reinforcement learning, right? So yeah, so but we want to verify that the controller is safe to use, and if you use this controller in this car, it will never hit the wall or something like that, right? So what we want is to design this model checker that will take this controller, let's say some neural network, and some model of how the environment behaves, let's say differential equations or some equations describing how the environment changes state, and some specification, let's say a set of safe states that you do not want to that you always want to stay in. And then you want to prove whether this is safe. So the model checker would say, okay, I can prove that that the car will never hit an obstacle, or it can, or you want a counterexample saying that, okay, it will go and hit this wall when these things happen and things like that. So as I mentioned,
this is for a fixed building, is it a fixed environment? I mean, a fixed
yeah. So you have
location.
yeah. So I'm getting to that. So yes, it's not really, but it's, yeah, we wanted to generalize the results. So yeah, so this works tries to do two things. First is this long horizon thing where we have this issue of increasing over approximation errors, preventing us from verifying for long durations. And the other is this verification, right? Let's say we go, this is a racetrack, and then you say you verify that the car is safe on this track, right? But then you go to this different track, it uses a lot of the same segments as in the first track, and the car is probably fine here, but then you don't have the verification guarantee for this track. So we actually want to train and verify a controller that works for multiple different tracks, right? And it's sort of, but you cannot do for all realistic environments. That's just, yeah, that's probably too much. But we consider sort of simplification. We say that, okay, you have these segments, right? Let's say you can have a straight segment, right, sharp left. And what we want to do is to train a controller and verify that it is safe for any track that is sort of made up of only these segments. Does that make sense? So you can construct infinitely many tracks using these segments. Also, the straight segment can be of any length and so on. Then you want to show that it's sort of safe in all such scenarios. Right?
Okay, so you say kind of locally prove that you go safely at each of these segments, is it?
Yes, yeah. So that is the whole point. But then you also need to stitch these results together, right? So yeah. So basically, that's all this work is about. So you have this environment which sort of denotes what are the different segments, and when does a segment end and things like that. Is something that the user specifies. And you also have some specifications saying what is the initial states, what are the set of states where the car is safe and things like that. and you use some compositional approach to learn, very similar to what I described. So you would learn one policy for each segment, and then use the corresponding policy whenever you detect that segment. And once you train that, you need to verify the controller, right? So the natural way to do it is to simply verify that it's safe for each segment, right? So if you say, okay, whenever I start in the initial state of this sharp right segment, I'll always stay safe and I will end up reaching the end of the segment within a fixed time step, right? Within a fixed number of steps. And this is sort of a property that you can actually verify using existing techniques and tools, even if you have neural network controllers. However, you need to ensure compositionality. So for example, you start in the initial state here, but then if you look at this trajectory, you are not starting in the initial in an initial state in the next segment, right? So you sort of need to generate these pre-post conditions to verify. So that's exactly what we do. So here the issue was that you start in an initial segment, initial state in the sharp right segment, and you reach the end of segment. And then when you're transitioning to the next segment, which let's say is a straight segment, then you're not you're starting at a state that is sort of outside. So yeah, and you also need to argue about that state now. So what we do is we introduce these new sets. So we have this new preset that sort of contains the initial set of states, and we have this post set that is sort of contained in the set of states where the segment ends. Then all you need to show is that whenever you start in a pre-state, you end up in a post-state. And if you transition segments from a post-state, you end up in the pre-state of the next segment. And then all the verification results nicely compose and you don't have to worry about anything. But the issue is, how do we find these pre and post sets? It's sort of hard to design them manually. So sort of we have some way to synthesize these pre-post conditions from simulations of the system. And we just use those sets for verification in the end, right?
Sorry, Kishor, in that previous one, so at the end of this sharp turn, right? What is what is the LiDAR see at the end of that?
It just sees the LiDAR reading. So it
no,
has,
what is is that the end of, is there a wall or there, or what does it see?
It just keeps continuing onto it's just a track, right? So
okay, so then you're actually not verifying it for this, you're saying that there is some extension there also but you're going only up to this point.
Yes. So, but but the verification result still holds, right? Because
so you can't compose this unless the thing that you join it with has, as much that you're showing that the LiDAR is reading at the end of this segment.
Yeah. So you assume that you at least have the LiDAR range afterwards. So so you cannot have
you can't just compose, right? You need some.
No, but all of these segments have that property. If you look at it, all of these segments have an initial.
So for example, I can't compose a sharp right with a sharp left.
You can, because after the sharp right, the sharp left also has an initial straight segment.
Okay, so you need a minimum length that the LiDAR has to. The LiDAR should not be able to see the end of the sharp left.
Yeah, but our LiDAR range is really small. It's like 5 meters, and also like these segments are, just long enough. So shorter than that, if you make these segments shorter, you cannot really even control it because it's too short, right? So in sort of most tracks, you can actually get those points.
Yeah,
right?
okay, but I think that's also a reasonable assumption that you have some overlap of some 5 meters.
Yeah, exactly. So all of these segments, when they start, they have at least like a 5 meter straight, right? But yeah. So you would sort of, if there's a sharp right after sharp left, you sort of at least when you're actually decomposing, you'll cut it down in the middle and make sure there's space. And if there's not enough space, I think even controllability is an issue because you cannot really do maneuver that much in that car. But yeah. So yeah, so we synthesize this automatically. So to recap, we synthesize these pre-post conditions and verify them using an existing tool. And this is some of our results on verifying the system using a neural network controller. And we split the verification instance into a bunch of different instances in order to parallelize the verification. And on average, an instance takes a few hours to verify, so it's not really that bad for the F110th car, which is sort of a complex car, uses LiDAR and all that. So yeah, so this enables sort of verifying long horizons. Actually, if you think about it, you can have arbitrarily large tracks, and the verification results still will give you a guarantee that the car will be safe. And it's also, it also generalizes to many tracks as opposed to just one particular scenario. So I think we are out of time, but I can take questions if you have, or if I can take more time, I can briefly discuss some future work.
Yeah, I think it's better you discuss future work. I think we have taken enough questions. So maybe you can discuss future work for a
Okay.
few minutes, and then.
Yeah. So overall, I think this phase of using form methods for machine learning is gaining a lot of traction. It's like so many people working on it now. And there are actually a lot of very interesting problems. And sort of what I focused on is trying to improve certain aspects of reinforcement learning, which is this data efficiency and usability, using replacing reward functions with specifications, and reliability, for example, is achieved by improving verification algorithms and so on. So there's some of the papers. So one thing that I haven't looked at and is actually very interesting is to study the sort of same problems that I've been working on in the offline reinforcement learning setting. So reinforcement learning, people are starting to observe that it's very sample inefficient. So if you want to learn to perform something on a real robot and you don't have a simulator for it, then if you actually have to interact with the robot to learn something about the robot, the current algorithms take close to like 1 million samples or some million steps of interactions, and that would take many days to achieve in an actual real robot, right? So it's not really that practical when it comes to applying it to robots and things like that. So what people are looking at is offline reinforcement learning, where you know that you have some data set from past interactions, right? People have been using these robots and studying with them and using all sorts of controllers. So you already have a big data set of interactions with this environment. And offline RL just tries to use this data set to either reduce the number of new samples that you need to collect, or to completely train a new policy without any new samples, right? Just understand how the robot behaves from the data set, and then just compute a policy to do something new without really having to interact in an online way. And existing RL algorithms really require the online interaction, because they actually pick what actions to do in every state in order to actually explore efficiently. So sort of figure out different actions in different states and things like that. But in the offline setting, you cannot really do that. And there are some ways to, and there's a lot of work on offline RL by itself. But in this setting, you can think of a few problems. For example, if you have a data set of interactions, and if you know that all of these interactions sort of denote a particular task. For example, there's someone actually controlling the robot and doing certain things, and then you just have this data, then you can actually try to study this problem of how do I actually explain what the task is, right? And there is work on actually trying to infer reward functions from such data. But again, as I said, reward functions are not the right way to think about a task or a specification, right? So you can think about synthesizing specifications from data demonstrating a particular task. And and you can also think about using this high-level specifications to do things in a compositional way, similar to what I did with the verification and the learning. So can you actually, if you have some specifications, can you take the data set of interactions and identify paths where certain subtasks are being done, try to learn them separately, and then stitch them together later and things like that. So that's again a line of work that sounds interesting. And in general, specification is not something that you worry about when you're looking at machine learning systems, right? So when it comes to traditional software development, right, specification sort of is something, I mean, still not thought about that well, but you at least write unit tests, and in some cases you also write some specifications, some pre-post conditions and things like that. But that's something that you usually don't think about when training neural networks. I think that's a good sort of way to think about having reliability in ML systems. So if you look at a typical ML engineer, engineer would take the data, would pick some learning algorithm, pick some model architecture and whatnot, and then get a model. However, this sort of figuring out the right architecture and what hyperparameters to pick and things like that is very time consuming. And also the model is sort of very opaque. You typically have no guarantees. It's often hard to analyze, interpret, and things like that. So sort of this paradigm of specification guided learning sounds interesting, where you have the engineer also write some sort of formal specification. They don't have to be complex or something like LTL, but something formal saying some very specific property that has some meaning about the model, and then try to incorporate that formal specification in the learning and ensure that the model actually satisfies such specifications, and sort of more like writing unit tests and software development. So, and this can have a lot of benefits, right? So you can enforce additional requirements on the model. For example, in RL, you can encode, in reinforcement learning, you can encode additional safety constraints, for example, right? If you want to do a task, but then you want to say the robot must never do this, then you can, like, if you have a way to incorporate such information in the learning algorithm, then that's actually very helpful. And then it can also help reduce human effort. For example, in the reinforcement learning setting, we were able to infer reward functions automatically from the specification. And finally, you might be able to generate models that are more interpretable and verifiable. For example, in the RL setting, we were able to split the final policy into a lot of small ones that had some meaning to them and were easier to verify and things like that. So, I mean, a problem that is well studied that actually fits this framework. This is not something that I worked on, but you might have seen these adversarial robustness examples where you have a neural network that predicts or stops incorrectly, but by adding very small noise to the image, it changes the prediction drastically, although the image looks pretty much the same, right? So, and there's a lot of work on trying to actually enforce that the neural networks don't have this behavior, so they're actually robust to such perturbations. But actually training them requires incorporating this additional formal specification into the learning process, which is the set of inputs, for example, the stop sign image, at which you want the model to be robust at, and the set of transformations that you want the model to be robust against, right? So and an area where this is relatively less well studied is this modern LLM stuff, where you have large language models generating code and things like that, and these are just trained on GitHub data and online code data and whatnot, right? And they don't really incorporate any sort of formal specification during training or inference or anywhere else, right? So you might think about adding something like, can I add some assume and assert statements before and after, and try to modify the training and the inference procedure to actually ensure that the code generated actually satisfies such things. And the problems involved, how do you actually incorporate such things in training, and how do you actually modify the inference procedures. So actually the inference procedure involves generating generating a lot of different candidates and picking one based on some score. But then you can actually use existing static analysis or testing methods to assign like scores that sort of enable you to pick the right piece of code that you want for the particular scenario. And this is also being studied a lot these days, which is to learn to output that the code generated is actually correct, and then also learn to output the proof alongside the code. So you're not just outputting the code, but also some formal proof of correctness that can be checked by something like Coq or Isabelle or so on. So yeah, so with that, I'd like to conclude. There's actually a lot of interesting problems. I can talk more offline about the specific problems in reinforcement learning. And yeah, there's a lot of potential for collaboration, interdisciplinary research and so on. Thank you. Yeah, you can find more on my website.
Thanks very much, Kishor. That was a wonderful talk. Very nice results. I am sure there are many questions, but I think we should take them offline. By offline, I mean post the recording if Kishor has some time. So let's all thank Kishor once again for the wonderful talk.
Yeah, thanks for inviting.
Yeah.
Thanks, Kishor.
Thank you.